morning, students. So today we are going to see semiconductor devices. Okay, semiconductor devices and semiconductor also along with that. Semiconductors. Okay, so about semiconductors we should all know. I mean, less numericals are asked, but more will be theoretical questions from that. Right. So what basically is a semiconductor? Semiconductor is those kinds of elements which have conductivity in between conductors and insulators. Okay, they have conductivity in between these elements, have conductivity. Conductivity of what? Current, electric current in between conductors and insulators. Conductors and insulators. Now insulators, we all know that they don't allow current to flow through them, whereas conductor readily make current to flow through that. But semiconductor is not like that. Okay, semiconductor is such that it will not make the current flow as it's flowing in conductor. That means there are certain charge carriers, certain electrons are there, or certain charge carriers are there in semiconductors, but it's not like conductors. Okay, but we can increase their conductivity. As we say that when we are increasing the temperature in conductors, its resistance increases. Okay, in conductors, what we have seen? In conductors, if the temperature is increased, the resistance increases. But in semiconductors, opposite thing happens. When you are increasing the temperature, their resistance decreases. That means their conductivity increases. Okay, conductivity increases. Conductivity increases. Right. So what happens? What these semiconductors are? We say that these are group 14 elements. Okay. Semiconductors are group 14 elements. And which elements we are talking about as semiconductor? Two elements we will be talking mainly about: germanium and silicon. Germanium and silicon. Okay. Both are group 14 elements. Their valence is 4. Okay. So in semiconductors, actually what happens? Or for that matter, if we are going to define conductors also, in conductors or semiconductors or insulators, okay, the outermost electrons mostly are found in valence band. Okay, so if you make a valence band over here, this is suppose valence band. Okay, this valence band, mostly electrons will be found here, and above this we have a conduction band. So in case of conductors, there is no difference here between conduction band and valence band. So that's why we say in conductors there is availability of free electrons, right? Because electrons can readily jump over here and participate in conduction of electricity. There is no gap here. Okay. The gap between this conduction band and valence band is called what? Energy gap. So energy gap is not there in conductors. This is conductors. Okay, whereas if you make insulators there is a huge gap. So this is valence band, and similarly we will have conduction band. Okay, it's like this. This is conduction, and this energy gap is very large, more than 3 electrons. Okay, so where it's very difficult to send electron from here to here. It's not that you can't, you can, but it is difficult. Whereas semiconductor lies in between. Semiconductor is in between here. This is your valence band in this one. Okay, and then this is the conduction band. So gap is small. This is energy gap. And we say that this energy gap is less than 3 electrons. So even at room temperature, some of the electrons can go to conduction band. Okay, even at room temperature, electrons move conduction band to participate in conduction of current. Okay, but still, here how many electrons are available? Here electrons available are very less. They participate in conduction, but conductivity is very less. Okay, in semiconductors. So our first purpose is to make this as a conductor. We want these semiconductors to behave like conductors. That is what this chapter is all about. Okay, so that's fine. Now, what type of conductors we have? We already said that there are two types of conductors that we are going to talk. That is silicon and germanium. Okay, what happens in them? Okay, if we talk about again two types of semiconductors, as I said, in that one also we have one is pure semiconductor and other one is impure semiconductor. Pure semiconductor means we are going to talk only about silicon or only about germanium. Okay, two types of semiconductors we have. Okay, what these are? Pure and impure. So pure semiconductor, what we have? We know that germanium is there or silicon is there. They have valency 4. So we talk about germanium. Okay, there's 4 valency. Okay, it will have the bonding with the next germanium because you have a crystal. Okay, crystal of germanium you have. So this side also germanium will be there. Okay, so what will happen if suppose we are going to heat this crystal? Okay, we are going to heat the crystal. Suppose from here these 2 electrons which are here. Okay, 2 electrons which are here, which are busy in covalent bond because you want to be in stable state. So you have made the covalent bonds over here. So when you are heating, suppose these 2 electrons got free. Will all the electrons get free? No. Only some of the electrons get free. So when these 2 electrons get free, these 2 electrons, because of thermal agitation, their kinetic energy is more, they jump from valence band to conduction band. Okay. So they are going where? Into the conduction band. So they go to the conduction band and they participate in conductivity. But at the same time, here what created? Here holes are created. Vacancy, hole is created. Where it is created? This is created in valence band. Okay, so if you make over here in conduction band, I'm just showing you these 2 electrons only. Okay, in conduction band, you have got 2 electrons. But at the same time, in valence band, you have got 2 holes. Okay, so conductivity of the current is going to happen here also and here also. Here how? Because when these vacancies are created, so surrounding electrons or neighboring electrons rather, which will have slightly more energy, slightly more kinetic energy, they will jump here. They will jump to fill these vacancies. Okay, so because of that, what happened? Motion of charges happen, motion of electron happen, and that will also constitute current. Okay, so in valence band also current will be there, and conduction band also current will be there. Okay, conductivity is found in both conduction band as well as valence band. Conduction band, who's making this conductivity? Electrons. And valence band, who's doing? Holes. Okay. CB, electrons are responsible for conductivity. Okay, in valence band, holes are responsible for conductivity. Right. Now, number of electrons created in conduction band is exactly equal to number of holes in valence band. Okay, because earlier nothing was there. There are no electrons. So, number of electrons here are 2, number of holes here are 2. So, we will say that number of electrons and number of holes are equal number of electrons created in conduction band is equal to number of holes in valence band, that is Ne equal to NH. Okay, now if you want to know that what is the charge in this one, suppose that conductivity is because of this also and conductivity is because of this also. So if we say Ni into Ni, that is equal to Ne into NH. Conduction band and valence band. So Ni square is equal to Ne into NH. Okay, Ni square equal to Ne into NH. On this one also sometimes question is asked. So we should be able to find out. What is this? Effective number of charge carriers is equal to Ne into NH. Ni square equal to Ne into NH. Okay, so this is pure semiconductor. Then we have impure semiconductor. Impure semiconductor means is we are going to mix something in them. Doping we are going to do. Okay, so impure semiconductor. Impure semiconductors. Now, why we are doing this impurity? Why we are mixing it? The reason is because in pure semiconductor, yes, definitely we got certain electrons, we got certain holes, but still their conductivity is very, very less. Their conductivity is very less. So we want to increase that conductivity, and because of that reason only we are going for impure semiconductor. So in impure semiconductor, what kind of impurity we can mix? Which is very similar to group 14 elements. Okay, so what we can mix? Group 13 or group 15? Because they should be almost same, right? Almost equal. So group 13 and group 15. That means pentavalent or trivalent. Okay. Pentavalent impurity we add. Pentavalent or trivalent impurity is added with germanium or silicon. Okay, now when you are going to add pentavalent impurity, you know already that germanium has valency 4. So if you have pentavalent impurity, the 4 electrons of that pentavalent impurity will make covalent bonds with 4 electrons of this germanium. Then one will be extra. So where will that one extra go? That will go to the conduction band. Okay. Suppose pentavalent means is phosphorus we will have. So phosphorus is here. Right. These are 4 electrons here. 4 electrons are engaged here are for phosphorus. Okay. 1, 2, 3, 4. Now extra. One extra is here. There's one extra. One extra electron. Okay. This electron moves to conduction band. This moves to conduction band. Okay. So in conduction band there will be plenty of electrons because it's not that we are going to have one bond only over here. We'll mix certain amount of phosphorus and germanium, certain amount. So it will have many atoms, right? So when you are going to put many atoms into that one, so that many electrons will be there that will go into the conduction band. Okay. So in conduction band there will be many electrons. Okay. So here is our conduction band. Let's see. So in this one now there is availability of electrons. There are electrons. Okay, this is conduction. Now in valence band what is happening? Now in valence band also because of thermal agitation, because of room temperature, there will be electrons as well as holes created. But not these many. Okay, in valence band, this valence band here, certain number of holes created. Okay, electrons also created, electrons jump to this one. Because we know that because of thermal agitation, whatever number of holes are created, same number of electrons also will be created and electrons goes to conduction band. Okay, now this one here, this impurity, all this is donor impurity because it's giving you extra electron. This is called donor impurity. Okay, so its energy level used to be very close to conduction band. Used to be very close to conduction band. Okay, that is why when you are having one free electron, it readily goes to conduction band because energy gap is very less. Okay, it's very easy for it to go over here because energy gap is less. You see that? That's why this is readily available in conduction band. Okay, so this is how energy differences we can show as far as donor is concerned. Okay, so what we have got now? We have got plenty of electrons in conduction band which are going to participate in conductivity, and we have certain holes also in valence band that are also participating in conductivity. Okay, but as far as neutrality is concerned, see, if you go back and talk about pure semiconductor, in pure semiconductor, there is in this valence band because of the thermal agitation, certain number of electrons become free, they go to conduction band and there are holes in that one. Okay, so still this is one crystal only. In this crystal, any charge is there or this is neutral? It's neutral. It's neutral, still neutral. And then still here we are saying Ne equal to NH also. Okay, now let's talk about impure semiconductor. Now impure semiconductor also when you mix these two, this was neutral and this was also neutral. Now this is one. Okay. Now this is what we are getting. You are getting electron and conduction band. There are holes in valence band. Is it still neutral? Answer is yes. It is still neutral. Still neutral. There is no doubt about that because this was neutral and both were neutral only. Okay. So here also this is neutral, and in this also we still have Ni square equal to Ne into NH. Okay. It's valid. Ni square equal to Ne into NH is still valid here also. But in this one, there are more electrons. So electrons are called majority charge carriers. Electrons are majority charge carriers. Majority charge carriers. Okay, and holes are called what? Holes are called minority charge carriers. Holes are minority charge carriers. Okay, for conductivity, you have this formula. Remember always, Ni square equal to Ne into NH. Whatever type of semiconductor we have, we will multiply. We will use this. So this is your impure semiconductor. Which one? When you have added pentavalent impurity. Now trivalent impurity, what is it? And this pentavalent impurity, when we have added, what we call this as N-type semiconductor. Why? Because in this one, electrons are mainly responsible for conductivity. Electrons negative. So this is called N-type semiconductor. N-type semiconductor. Okay. Now let's add trivalent impurity. So when trivalent impurity is added, trivalent impurity is added. Okay. Now in this one, what will happen? 4 electrons of germanium will make the bond with 3 electrons of trivalent impurity. Okay. Then what will happen? Now because of that, there will be one covalent bond will not be making. So because of that, their vacancy is created. There is a vacancy. Okay. So germanium is like this, and here what impurity should we add as trivalent impurity? Okay. Indium is pentavalent. Okay, fine. Aluminium. Okay, fine. So whatever that is, leave it at aluminium or indium, whatever. Okay, so trivalent impurity is there. Now, this has 3 electrons on it. The 3 electrons are going to have covalent bonding with neighboring germanium. This is 1, this is 2, and this is 3. But now here electron is there, but here electron is not there. Electron I should show, so right? This holes I should not show. Because if I am showing holes, then you can have confusion. So let's show the electrons. Here is electron, here is electron, here is electron, and here is electron. Here electron, and here electron. But here electron is not there. Here electron is there. Here electron of germanium is available, but here there is nothing. So there is vacancy. So this vacancy now will make neighboring electrons to jump over here. Right? And if suppose that we have added so many atoms of this impurity, so many vacancies are there in that. Okay, so because of this vacancy, conductivity will happen in this. Where will be vacancy? Near valence band. Okay. So here it is. This is valence band of germanium. Okay. And in valence band again, because of thermal agitation, something will happen or not? Definitely will happen. So in this valence band, you can keep some holes because of thermal agitation, right? And there is conduction band also. There is conduction band here. In conduction band, there will be certain electrons. Yes, these electrons will be here. Okay, then where is this trivalent impurity? The trivalent impurity is here. Here it is. Okay, this is the energy level of trivalent impurity. Okay, it's here. Now what happens in this? Because where are actually holes? Holes are here only. Where are holes? Holes are here. This is the energy level of impurity. What we call this is acceptor impurity. Energy level of acceptor impurity. Acceptor impurity. Now here you see energy gap is very less. Okay, so this is very close to valence band. And that's why we say that in this one more conductivity happens in valence band as compared to conduction band. In the previous case, what was there? The energy level was very close to conduction band here. So here mainly where was conductivity happening? In conduction band. But in this case, where is conductivity happening? Valence band, because this energy level is very close to valence band. Okay, and this is called what? This is called acceptor. impurity. And since in this one there are more holes, because there are plenty of holes in this impurity that we have added, plenty of holes there, and these holes become majority charge carriers. So here holes are majority charge carriers. Holes are majority charge carriers, and electrons are minority charge carriers. Okay, electrons are minority charge carriers. Minority charge carriers. Right. In this one also, our relation is valid. Yes, it's valid. And in this also, a crystal is neutral. Yes, because charge is not lost. Nobody has taken electron, nobody has given us electron. Crystal was neutral before also. Crystal is neutral after that also. Okay, so Ni square equal to Ne into Nh. Now, which kind of semiconductor we call this as? We call this as p-type semiconductor. Because in this one, holes are leading. They are responsible for conductivity, and holes are considered to be positive. Okay, positive as compared to electron. So we call this as p-type. P means positive, positive type semiconductor. So now we understood that when we talk about conductivity through semiconductor, we need to have impure semiconductors. Okay, we need to have impure semiconductors, then only we can take or we can replace them. We can replace them in place of conductors, right? So this is semiconductor. Now we are going to make diode from them. PN junction diode. PN junction diode. PN junction diode means one P-type semiconductor is joined with N-type semiconductor. We diffuse with N-type semiconductor. So we make the symbol for this is like this. This is P, this is N. Okay. And what happens if we are doing it like this? Suppose this is P-type here and this is N-type. Okay. Okay. One is P-type, another one is N-type. This is P, this is N. Now P-type semiconductors will have more of holes in this one. We can make holes. Right, and here will be electrons more. These holes are in which band? Valence band. These electrons are in which band? Conduction band. So here more concentration of electron is there, here more concentration of holes is there. So because of concentration gradient, what happens is these electrons will start moving towards the junction. Okay, they will start moving towards the junction. So what will happen? These electrons will come over here. And here what they will create? Holes. This side relatively become positive because electrons from N side means N side is neutral or not? N side is neutral. N-type semiconductor in general is neutral. P-type semiconductor is also neutral. Okay. But here more availability of electrons is there, or you can say electrons and conduction bands, they have more energy, more kinetic energy. Okay. So they diffuse to P sides. So when they diffuse to P sides, this N-type semiconductor has lost electrons. It has become positive. And P-type semiconductor has got electrons, it becomes negative. So because of this, what happens? This is diffusion. Because of this, what happens? Near the junction, okay, near the junction, right? So near the junction, if I am going to say, I'm just removing this one from here now. So near the junction, what happens? Here you can see holes. From where these holes are just, we are trying to show it that because electrons are moved this side, so here holes are created. Okay, and here electrons are there. So because of this, this became positive and this became negative. Inside here, okay, there will be electric field like this. And this here is called depletion layer. Okay, depletion region you say or depletion layer you say. This is created. Now what this is going to do? This is going to oppose the further motion of these electrons. Okay, because this is electric field now. Electric field is like this. Initially, these electrons moved this side. They diffuse this side. Higher energy electrons diffuse this side. And they, because of that, they created one depletion layer. Okay, because this side became positively charged, this has become negatively charged. So they create one depletion layer. And because of this, from positive to negative, there is electric field. Okay, and because of this electric field, what is happening now? Electrons. If electrons are going here, these are higher energy electrons. Electrons are going this. But because of this electric field, they are repelled to go in this direction. And these holes also. These holes wants to move to this side. So because electric field is in this direction, these holes are again repelled. They go this side. So there is no motion of majority charge carrier is happening. Okay, majority charge carriers are not able to move. Higher energy, very high energy electrons are there. They may move. They may move, but mostly electrons are not able to move because of this depletion layer. And depletion layer is there. Electric field is there. So there is potential difference also, and that potential difference we call as barrier potential. Okay, so potential difference across this. Call this as barrier potential. Okay, and this is what diffusion. So because of diffusion, one current will come. That current is called diffusion current. Diffusion current. Right? Now, in N side also, do we have small numbers of holes? Answer is yes, do we have it. And in this P side also, we have small number of electrons. Yes. So there are electrons here, and there are holes here. And what are these? These are minority charge carriers. These are minority charge. Now, when this electron goes to towards this junction, because of this electric field, this electron moves to this side. Okay, minority charge carriers can move this side. Correct? Clear? And if suppose that any covalent bond here, this covalent bond here, breaks, any electron and holes are becoming free, then what happens? Electron will start moving this side because electrons are here, P side. So electrons will be considered as minority charge carriers. So they will also move this side. So because of this, because of the motion of minority charge carriers, we are going to get a drift current. Okay, this is because of majority charge carriers. Majority charge carriers. Okay, then because of this barrier potential or because of this depletion layer only, minority charge carriers are able to move this side. Then this current is called what? Drift current. Okay, so due to barrier potential, minority charge carriers move from minority charge carriers, electron only we say, electron move from P type to P side to N side and cause drift current and cause drift current. Okay, Now let's try and understand. When we made this PN junction together, immediately what happened? Diffusion current. Diffusion current initially was very large because suddenly they jumped. But slowly, as the formation of depletion layer is taking place, slowly, the diffusion current decreased. It will not become zero because still there are higher energy electrons, they will still be able to. So it will not become zero. But once this depletion layer came, barrier potential came, from here also minority charge carriers also start moving inside to that side, which constitutes drift current. And one stage will come when diffusion current, when which electron is moving from N to P, and drift current in which electron is moving from P to N become equal. So net conductivity becomes zero. Net current becomes zero. So when diffusion current and drift current are equal, our diode is ready. Okay. Diffusion current is equal to drift current. Okay. Net current is zero. Now what? Diode is ready. So far it was not ready. No. Diode is ready. There is no current in that. Right? It's ready to use. Now how to use this PN junction diode that we have made? We know that two types of biasing is there. One is forward biasing and another one is reverse biasing. Okay. So forward biasing. Forward biasing, what we do? P-type semiconductor we connect with the positive terminal of the battery, and N-type we connect with the negative terminal of the battery. Right? Okay. Right. So this is our, here we will make a junction because that we have to show our depletion layer. Okay. This side is P, this side is N. Still we can show holes here. Okay, some electrons also we can show. And here there are more electrons than holes. And this is our depletion layer. Here electrons are here and here holes are here, like this. Now what we did is we connected this with battery. Battery, this is positive. And this is connected with negative. This is forward bias. So because of this forward bias, what happens? This is positive terminal of the battery, this is negative terminal of the battery. So there is external electric field. Because we know that if suppose we say that this is 0 volt and this is V volt here. So here also V volt will come and here is 0. So between this V and 0 there is external electric field. Its direction is from left to right. And inside here, depletion layer, we know that one small electric field is E. Now as compared to E, E is very small. So because of that, what will happen? The depletion layer will start decreasing. It will start decreasing. Okay, this will become smaller, smaller and smaller. And because this electric field is huge, so because of this electric field, our electrons will start jumping here. Okay, electrons will start jumping. And in this one here, in valence band, in p-type, when this electron jumps over here to here, what happens suddenly? We all know that this n side becomes positive. Yes or no? This n side becomes positive. So what happens to overcome this p side? P side, because you are applying electric field, right? Electric field is applied. So in p side, covalent bonds are broken. So when here covalent bonds are broken, okay, here electron is there. Where electron will go? Electron will go this side, no? This electron. Go here. We go to the positive end. A positive end battery will do the work. It will make electron to go like this. Electron will go back to N. Because you have to maintain that neutrality also at the same time. So battery is not there which is going to make them P type or N type. They are already there. Okay. But it will try to maintain the polarity. So when electron jumps over here to here, then what happens? Here covalent bond is broken, one new electron becomes free and it will go over here. So in that way, current will be maintained. This became smaller, no doubt. Here also covalent bonds will be broken. Yes, that also is there. So all the things are happening at the same time. But will this depletion layer become zero width? No, it will decrease. It will never become zero. Okay, that electric field will always be there. Which one? ED. Okay, so what's happening in this? Two things I told you. One, external electric field we have set up. Electric field, external electric field is in opposite direction to this depletion layer electric field. Okay, because of that what happens? Electrons can move. Okay, once electron is moving this side, from here, covalent bond is broken and electron goes here so that the supply is maintained. Second thing, here in depletion layer also some covalent bonds are broken. So because of this electric field, what happens? Electron goes to this side, hole goes to this side. Okay, then again electron will be jumping over it because of the external electric. So in all this, our current, the conductivity is maintained. This is forward bias. Okay, but in this also, if suppose that this external electric field we are increasing slowly, when exactly the current will start? When our electric field is becoming greater than, then only we are going to get the majority of current. So if we make the graph, okay, we make the graph for this one. Right, this is current. Okay, and here is potential. Potential means external potential that we are applying. So initially, when V is 0, do we get the current here? Yes, we have, but very less. I mean, diffusion current and drift current are almost equal. Okay, so there is no current as such. So from where it will start moving? When external potential difference becomes equal to barrier potential. So it will be like this. It will be like this here, and then again it shoots. Okay, suddenly current increases. So this is what? This is barrier potential, you say, cutoff voltage, you say, knee voltage, you say, anything we can say, or knee voltage. Okay, for germanium, this value is 0.3 volt. Now, sometimes it becomes necessary to remember that because this information certain times is not given in the problem. So, it's better to remember germanium it is 0.3 volt and silicon it is 0.7. Okay, this is forward bias. Then we have another one, reverse bias. Reverse biasing. And this one what we do? We connect p-type semiconductor with negative terminal of the battery and n-type we connect with the positive terminal of the battery. Okay, what happens in this? Very simple to understand. It's not tough to understand that. This is our depletion layer. Okay, so this is p-type, this is n-type, and we connected this with the battery. It's like this. Okay, p-type means holes are there, and n-type means electrons are there. Okay, majority charge carriers we have made. Then here electrons will be there, minority charge carriers. And here holes are there. This depletion layer. Here electrons, here holes. So depletion layer you have electric field like this. Now what you did? You connected positive terminal over here. If here is V and here is 0, then this will be V here and this will be 0. Now, where is the external electric field? External electric field is like this. Now, what this is going to do? This is further prevent any type of diffusion of electrons which is going to happen, because this electric field is like this. So, these electrons obviously will go here. Okay, we come to the battery. Battery will make it over here. Battery will supply over here. So, this holes are there. They will also be make the bonding with these electrons. So, this what because of this what will happen? Depletion layer will keep on increasing. Depletion layer will increase. Reason, because from here electrons have come and they have fused with this. So now there is no further electrons or holes which can go from here to there, except minority charge. So this electrons are here. Electric field is like this. So this electron, being a minority charge carrier, can move. So initially you will get only very small current because of these minority charge carriers. But other than that, nothing is there. Nothing. Now what to do? Now nothing we have to do. We have to just increase this potential. So because of this, what happens when this minority charge carriers are there? They'll move fast because of this electric field. These electrons will move fast. So when this move fast, while moving, they collide with these already covalent bonds are there, no? These electrons and holes. They'll collide with them. When they collide, then they break their bond, and because of that, pair of holes and electrons are created. And because of pairs of holes and electrons are created, suddenly there will be certain amount of current flowing. So when this collision happens, we call this as avalanche. Avalanche breakdown, you say. Okay, and we get current. So mainly current in this reverse bias is not because of the majority charge carriers, it is because of minority charge carriers. Minority charge carriers. Okay, so current is because of minority charge carriers. Minority charge carriers. Okay, whereas in forward bias, the current was due to majority charge carriers. Current is due to majority charge carriers. Okay, and the current that we get, its range is in milliamperes. Okay, let's say I in milliampere. Which type of current is this? This is in the direction of diffusion current. Okay, whereas in this case, what is the direction of current? This is in the direction of drift current. Okay, in the direction of drift current. The drift and diffusion are in opposite direction. Diffusion is in one direction, drift is in another direction. So if we are going to show the VI characteristic of this reverse biasing, it will be in opposite direction. Okay. Right. So it's in opposite direction. This is I here, and this is V. Now V we have applied in opposite direction as compared to the forward bias. So that's why we are showing it in this way. So how is the current then? Current is like this. Small drift current is there. Small drift current is there, but suddenly it becomes two types of current we are going to get. One is Zener breakdown and one is avalanche breakdown. Avalanche, I told you what happens is covalent bonds are broken. Now Zener breakdown is also one thing. What is Zener breakdown? Zener breakdown means is when you are giving too much doping, very highly doped P-type semiconductor and N-type semiconductor, they're very highly doped. So in highly doped also avalanche is only going to happen. We call it as Zener. When? When they are highly doped. When they are lightly doped, we call this as avalanche. This is lightly doped. Okay. When they are heavily doped, when conductors, not conductors, semiconductors, when semiconductors are heavily doped, breakdown is called Zener breakdown. Zener breakdown. Okay, and the current that we get here is in microampere. So a lot smaller than what we got in forward bias. Okay, because this is involving minority charge carriers. There we have majority charge carriers. So this is reverse biasing and forward biasing. Now Zener diode we show like as PN junction diode we showed like this. This is our PN junction diode. Zener diode we show like this. Okay, this is Zener diode. Right? Now usage where we are going to use PN junction diodes. Okay, what are the uses? What is the applications? So uses are uses. Let's say first we talk about LED, light emitting diode. Okay, light emitting diode what we have? That should be a diode, that is PN junction diode, and it should emit light, LED. So how it is? It's shown like this to us. Okay, these are photons. This is how photons are shown, right? This is the symbol through which we show LED. What happens in this? Very simple process. High energy electrons. Okay, when high energy electrons, you are connecting this in forward bias. Okay, first thing is it's connected in forward bias. It's connected in forward bias. Right. When you're connecting it in forward bias, and if you make it right, this is our depletion layer. This is P, this is N, connected with the forward bias. That means what we want, diffusion to happen, yes or no? Yes, diffusion we want. We want diffusion to happen. When diffusion happens, these electrons move to the P side and diffuse in the hole here. Diffuse in the hole. So when this N means is you have electron in conduction band. Conduction band means is high energy electron. When it is going to diffuse with the hole here, where is the hole? P side. Where hole is found? Valence band. So it's on lesser side of energy. So when there is diffusion is happening, when these electrons are moving and diffusing with this one, so obviously they will release energy because they are jumping from conduction band to valence band. They are jumping from conduction band to valence band, so they will release energy, and that release in energy only we are calling as photon. Like this. Whenever diffusion is happening, you are getting a photon. Correct. This is happening. Then you will say that all the electrons will go this side. As I told you, when electron moves from here to here in P side, immediately one bond is broken. Electron and hole pairs are created. Electron will go back over here. Continuity will be maintained. So these electrons will come again over here. they fuse with the hole, again one photon is created. So like this, we are continuously, LED bulbs are there, no, they are giving us continuous light, or they will give light for some time and then they stop. No, continuous. It's a continuous circuit. Will keep happening. Okay, this is LED. LED mainly is release of photon. Now we know that in atoms we already have studied when the electron jumps from higher energy orbit to lower energy orbit, photon is released. Here also the same thing. So this is LED. Okay. What are the advantages? Many advantages are there. You all know that. LED's main advantage is there. As you switch on, immediately this also switches on. Earlier it was like when you used to have tubes. You switch it on, then they will fluctuate for certain time and then only it will switch on. Okay. But LEDs are immediate, very light, reliable, can even work under the less voltage, fluctuation of voltage also. Okay, and durability is more. So these are all advantages of LEDs, or a normal bulb, right? Okay, this is LED. Then what we have? Then you have photodiode. Okay, photocell, photodiode. A photodiode we get in, uh, you can say that opposite process of LED. Okay, and what happens in photodiode? We have reverse bias, and you can say that you have highly doped semiconductors. Highly doped semiconductors. Okay, now we have connected them in reverse bias. In reverse bias. So in reverse bias, we all know that their depletion layer will be very large. It will be large. Okay, and what we want in this one, we want that photons to fall on this one. Okay, we want photons to fall where? In depletion layer. So suppose depletion layer we are making big here. Okay, this is depletion layer, big one, right? And we have connected a reverse bias. So this is P side and this is N side. It's like this, right? So what we are doing now? Now photons are coming like this on the depletion layer. They are incident like this. Okay. What they'll do now in this depletion layer? What is there? Pairs are there. Electron and holes pairs are there. Okay. Here electrons will be there. Okay, like this, we have made more this time. Here holes are there. Pairs are there. Okay, so now what will happen? When these photons are coming, they will break this pair. So when this pair is broken, now what will happen? Now in this direction, you know that electric field is there. Because of this electric field, this electron will go here. These electrons will go here. Okay. So because of this, what will happen? Current will. If we have ammeter over here, we'll detect the current. We'll detect the current. Okay. This is photodiode. Now, what is the usage of this one? Now, this we use in remote controls. Okay. Photodiodes are used in remote controls. Now, whenever you switch on, immediately what will happen? You can see the bulb is glowing, right? Remote control. Burglar alarm. Okay. Automatic doors. Okay. And these photodiodes are used. Okay. When this is falling, you'll get the current usage. Suddenly, if not there, current will not be there. If somebody is coming in the path, current will stop flowing. Current will stop flowing, then something will happen. Okay, these kinds of sensors you can make. Photodiode is used for sensing, sensors. So remote control, burglar alarm, automatic doors, we can use photodiode, and this is the working of photodiode. Okay, and here also current is because of minority charge carriers, remember that. So it will be, if IV characteristic you have to make, then IV characteristic will be like this. Before when it is gone, like this. Okay, not be breakdown. I'm not going for breakdown in this one. Okay, it is coming because of the photons in the depletion layer. Bonds are breaking, and because of that we are getting the current. So it's not going to break down, but it will be like this only because it's a current because of minority charge. Okay. Then what we have, another use of this one is solar cell. Okay. Now what we do in solar cell? Solar cell. Now with the solar cell, we want to create the potential difference so that we can get current. So solar cell obviously will not be biased. No forward biasing, no reverse biasing. Nothing is there. Okay. Solar cell. Okay. It's also PN junction diode, and it is also heavily doped. Okay. We'll make this also heavily doped. This is our depletion layer. P. This is it. Right. And how it works? Here also photon has to come. Light has to come. It's coming. Again, what is broken? Bonds are broken in the depletion layer, and within the depletion layer there is electric field because of the depletion layer electric field, barrier potential. Okay, it's like this. So if here bonds are broken, let's talk about electrons alone. What will happen? Electrons will go this side. Electrons will go this side. Electrons will go this side. So what will happen? This here become more negative. Negative, negative, negative. And this side will go what? Holes. Holes will go this side. So holes are going this way. Okay, holes are going this side. So this side becomes more and more positive. This side become more negative. And we are connecting it. And suppose that we connect here a meter. Because of the potential difference created here and here, we'll get the current. We'll be getting the current. This solar cell. Okay, we did not connect any battery over here, no forward bias, no reverse bias. We made photons to fall over it. They have broken the bond. Electron goes this side, making this negative. Holes goes this side. So that means actually here the flow of electrons are happening even from P side. Okay, so this becomes negative and this becomes positive, and you can get current because of that. Okay, this is the principle on which solar cell works, right? Then what are the other applications, other uses? Other is rectifier. Rectifier you have. Now rectifier is what? Rectifier is a device which converts AC into DC. Converts AC to DC. Converts AC to DC. But okay. So what we do is take one transformer here. Okay. Connect AC input. It's like this, our transformer. And here we are connecting one PN junction diode. Okay. Here is output. Okay. Now one thing I didn't tell you. When we are connecting PN junction diode in forward bias, it works like a wire. It's circuits when we are going to see. Okay, PN junction diode in forward bias acts like a wire in circuit. Okay, and if it is in reverse bias, PN junction diode in reverse bias acts like open circuit. Acts like open circuit. That means current will not. So this is also a circuit only. Okay. So in this one, what happens when we are talking about AC? We know that half a cycle is positive and half a cycle is negative. So when we are talking about half a cycle positive, and we know that this will be positive here, this will also be positive. So when this is positive and this is P and this is N, so this is forward bias. So for positive half cycle, this is forward bias. Okay. So output we are going to get positive half cycle. Then when this is going to become the remaining half, now remaining half will be what? Remaining half means is this is going to become positive and this is going to become negative. Okay. First half this is positive, second half this is positive and this is negative. So when this becomes negative, now this becomes reverse bias. For second time this becomes reverse bias. So we are not going to get any current. Okay, stopped it. It is open circuit. Then again, because it's a continuous input, then again we are going to get something like this. Okay, so this is how we are going to get DC. This is DC, but only half of this is converted. Okay, and its average value already know 2I naught by pi. We know that. Okay, so average value we know. Time period is same. Frequency is same. Frequency we didn't change. Its frequency. Its frequency same only. Correct or not? Because in remaining half of the cycle nothing is happening. Okay, then. So this is how we are connecting or rather converting AC into DC. Now if suppose that we want to convert entire one, then we can have full wave rectifier. This is what? Half wave rectifier. This is half wave rectifier. The full wave means what? We will connect here also. Okay. So let's see. Okay. So again transformer. Here is one PN junction diode and here also one PN junction. That's all. Okay, and here is input. So in the first half cycle, this is positive, and this is negative, this is negative. So what will happen? This is PN junction. So this will conduct the current. We'll get it here. In the next one, this will become positive and this will become negative. So in that case, this is forward bias. So current will come from here. So then it will be like this. Okay. Half cycle is this one white and half cycle is this pink. Okay. Input is like this. This is input. This is output. So full wave is rectified. Yes, full wave is rectified. But its frequency has become double because it's repeating twice in one time period of this. This is not repeating. This is positive and this is negative. But here both are positive. So its frequency is doubled. Remember that. Okay. Frequency is double of This is full wave rectifier. So these are the usage. Okay. Now let's solve few problems on this one. How to solve problem? Let's see. Okay. So some of the problems we are going to see. Just a minute. Okay. So problems are like this. This is our thing. Earth. We have a resistor here. Make a PN junction diode, and here we connect with a battery. Okay. Let's say this is 10 ohm, and here is minus 5 volt. The question is asked from us: what is current through resistor? What is current through resistor? Now we all know that current will be through resistor only when this PN junction diode is forward bias. Otherwise, there will be no current because it will act like open circuit. Okay. So the question is first to check whether it is forward bias or reverse bias. Okay. That is the first question from us. Now you see that this is minus 5. This is 0. This is 0 volt. This is minus 5. So which is having higher potential? Say 0. So if 0 is higher potential, then definitely we can say this PN junction diode is forward bias. Definitely current is there. What is the potential difference between the 2 points? 5. Resistance is 10. Because if this is forward bias, it will act like a wire. That is it. Okay. So current value will be potential difference by resistance. So that is 5 by 10. 0.5 ampere. Okay. Like this questions are asked. Then one question we will do for Zener diode. Zener diode, I didn't tell you that where it is worked. Zener diode is used as voltage regulator. Zener diode is used as voltage regulator. That means potential across this will be constant always. Okay, and it is connected in parallel with the appliance. It is connected parallel with appliance, so that even if the fluctuation in voltage is there, voltage across appliance remains same because Zener diode's potential will remain constant. Okay. So how question will be asked from us? We'll be making it with a different color than here. Okay. So here this one resistance we'll make, and here we'll be making one Zener diode, and here your appliance is there. Okay. That's like this. Now let's put the value. Let's say this is 250 ohm and this is 1 kilo ohm, and here it's a 15 volt, and the supply let's assume is 25 volt. Okay. Our question is how much is current through Zener diode? Find how much current is passing through Zener diode. Zener diode. Okay. So now what we do, we know that here is 15 volt. So across this also will be 15 volt. Correct. Total is 25. So 15 is dropped over here already. That means across this is 15. So in this one, how much will drop? 10. So here will be 10 volt on. So we can find this current at least. Let's say this is I, and here goes I1, and here goes I2. Okay. So I we can find immediately. What will be I? I will be delta V by R, that is 10 by 250. 10 by 250 means 1 by 25 ampere. That's I value. Now I will try to find I2. Now across I2, how much is potential difference? 15 volt. Okay, here is 15 volt potential difference. Okay, so what is I2 here now? I2 is 15 by 1000. 15 by 1000. Okay, so we can write this as 3 by 200 ampere. Correct. Now what will be I1? I1 will be I minus I2. I1 will be I minus I2, or you say I equal to I1 plus I2, both are same. Okay. So I is what? 1 by 25. And this is 3 by 200. Okay, so what we are going to get? 5 by 200. So through zero diode, how much current is passing? 1 by 40. Okay. This type of question will be asked from us. Alright. Then what else? Okay. What else? Then we will have one question in different way. Okay. Suppose that the input is given to you in the waveform like this. Okay. This is minus 5 volt. This is plus 5. This is how the input is given. Okay. So what we have given the input? Input we have given to this circuit. Okay, this is the circuit for us. Right. This is your resistance. So how will be the output? You can say it's a question of rectifier. Okay, you are giving AC input to that, no? PN junction diode for rectifier. This is also AC input, minus 5 plus 5. Correct. So initially this is minus 5. First minus 5. So if suppose here minus 5, this is 0, and this is PN junction diode. So what will happen? Nothing will come. It will not give you anything. Correct. When 5 volt will be there, then this will be forward bias. Then again this will be negative. Again it will be reverse bias. Right. So how we are going to get the output for this one? 0, 5, 0. Minus 5 will not come. 0 because no current will be there. Then corresponding to 5. Then again 0. So how to make? 0, right? Then 5. Okay, constant be 5. Then again 0. Very similar to input only, right? But smaller because this is not minus 5. This is 0 plus 5, 0. This will be the output. Okay, very similar to how input was, but input was minus 5 plus 5. Here we are getting 0 and plus 5. You are not getting minus sign because that became reverse biased. Right? So these are the questions based on PN junction diode. Now, what we have in semiconductors, very small thing is there, we call this as logic gates. Okay, logic gates are basically what? Switch on and switch off. Okay, these are binary operators. Binary operators means switch off and switch off. Switch off and switch on. And we represent this with 1 and this with 0. Okay, logically we place them in a circuit so that it works properly. Okay, so three types of logic gates we have. We have OR gate, we have AND gate, and we have NOT gate. Okay, now input will be, normally we show input from 2 points and we say that this is A and B. So OR gate actually we show in this way. This is how OR gate we show. This is the input, this is the input. This input is A, this input is B. And output is Y. This is what actually A plus B. Now input, when we are showing, inputs are what? Either switch on is there or switch off is there. That is the meaning. Okay, 0 or 1. So if we show that truth table, always truth table is made when we are talking about logic gates. Okay, this is A, this is B, this is Y. So if suppose one switch is off means is 0, 0 input. B is on, then input is 1. 0 plus 1, that means you are still going to get the current. Okay, if you are getting input from A or you are getting from B, still your bulb is on. If this is 1, this is 0, then again 1 plus 0 is 1. If both are on, even then there is no problem. But if both are off, then answer is 0. That means this is kind of a parallel circuit. Okay, this is parallel circuit. Which one? OR. AND is like a series circuit. How to make it? Like this. This is AND. This is A, this is B. Now this is series circuit. Series circuit means what? If any of the switch is off, bulb will not be on. This is parallel. If one of the circuit is also working, then bulb will be on. Here, so here it's truth table. If you make, how it will be? A, B, Y. So this is on, this is off. This is off because this is series circuit. 0, 1, 0. 0, 0, obviously 0, but 1, 1. If both are on, then your bulb is also on. NOT gate is what? It changes the input. If suppose that input is coming as switch on, then it will make switch off. If it is switch off, it will make switch on. That means it is the property of NOT gate to reverse the signal. Okay, this is NOT gate. How to show this one? This one we show like this. Okay, or sometimes only this also will be shown dot. So what is the meaning of this one? If input, a single input is coming, not double input in that. So if input is coming 0, this is input and this is output. If 0 is coming, it will make 1. If 1 is coming, it will make 0. This is NOT gate, this is OR gate, this is AND gate. And then we have combination. Like if suppose NOR gate, we have NOR. The NOR means is OR, this is OR, and like this NOR. Now this will be NOT. Okay, or you can make it separately also, like this. This is NOR. So if this is A, this is B, this is here C, then here will be what? C naught, or which we are calling as Y. Okay. So if we make truth table here, A, B, C and Y. So what you will say? 0, 1. C will be 1. 1, 0. This will be 1. 0, 0. This will be 0. 1, 1. This will be 1. Now, negation. This is negation. That means it's going to reverse it. So negation means 1 will become 0, 1 will become 0, 0 will become 1, 1 will become 0. Okay. That is NOR. Same way we can make NAND. AND connected with NOT. So NAND is here. Okay, this is NAND. Either you can put a circle over here or you make it separately. Okay, this is A, this is B, this is C, and this is C dash. We know this is equal to Y. So what is this? This is A, this is B, C, and Y, which is C dash. 1, 0. This is 0. 0, 1. This is 0. 0, 0. This is 0. 1, 1. This is 1. Now negate it. 1, 1, 1, 0. This is NAND. Okay. So these are the combinations. So how many gates we saw now? 3, and this is here 2. This is what we have in our syllabus. Okay. So questions can be asked from you. How question we can make? This is the question. Okay. Okay, this is what? This is OR gate. And this is AND. Okay. Now what is there? We have 3 inputs here. This is A, this is B, and this is C. Okay, 3 inputs are there. Now suppose that here we want 1 as output. 1 means switch on. We want 1 as output. Then what should be the input signals? What should be input signals? Options are there. We can make the options for them. Okay. Options can be there. Suppose 0, 1, 0. Okay. 0, 1, 0 we can make. 1, 0, 1 we can make. C option and D option. Okay. Then C option we can make 1, 0, 0. And D option we can make 1, 1, 0. Okay. So out of that, which signal will give us 1 as output? Let's check. Now suppose that first one we are trying. Now in this one itself I am trying. Okay, let's see. 0, 1, 0. So if this is 0, this is 1. This is OR. So this is going to be 1 only. So here will come 1. Okay. Then C is what? C you have taken here 0. So this is 0. This is AND. 0 and 1. It will give you 0 only. That means this is not there. This is not working. Okay. Now let's go for the second one. Second one is what? 1, 0, 1. Okay. So this I have to remove. Huh? Okay. All right. Okay. Now what we have? 1, 0, 1. So this is 1. This is 0. 1 and 0. This again is 1. So it will be 1 here. And this one is 1. This is also 1. 1 and 1 will give us 1. Okay, this is our answer. This is correct. This also you could have checked. 1, 0. So this would have given you 1. But this is coming 0. So 1, 0 would have given you 0. This also you can check. 1, 1. 1, 1 means this is 1. And from here 0 is coming. So 0. Only one option is correct. Which one? B option. Okay. Like this question can be asked, then they can ask you directly truth table also. Find the gate. Okay. Find the gate. So let's see one question we will do like that also. Okay. So we'll try to frame one question. This is NOT gate. Okay. One NOT gate directly we are having. Here. Here we'll have AND gate. We'll have one more here. We'll make OR gate here. So NOT also done, AND also done, and OR also done. Okay. And this is output. We have to identify which gate is this. This is A and this is B. Identify the gate. Identify the gate. That is the question for you. Okay. So what we have to do now? Simple it is. Just make a truth table. Nothing else we have to do in this particular logic gates. Okay. Make the truth table. Make it here A. Make it here B. And then in between what is it? In between, if we will see that if it is more required, we'll make. And finally Y. Okay. So let's say this is 0, 1, 1, 0, 0, 0, 1, 1. These are the inputs. So 0, A is we have given 0. Okay. So A, if we have given 0 here is not. Not means it will become 1. So here comes 1. Okay. Here comes 1. B, A I have given 0. So B I have given 1. So this is 1. Here is also 1. 1 and 1, this will become 1. Okay, let's see what's coming from here. 0. So this is coming 0. This is 0. So 0 and 1, here becomes 1. So 0, 1 sensor is coming 1 here. Right. Next one, you see 1, 0. Check what is 1, 0 here. 1, 0 I'll be making with different color. Okay. Now this is 1 and this is 0. Now if this is 1, this is going to make it 0. So this is 0. Okay. This one is 0. This is also 0. 0 and 0 will give you 0 here. From here what's coming? A was 1. From here is coming 1. 1 and 0 will still give you 1. So here 1. So for 0, 1 is also 1. 1, 0 is also 1. So look like OR gate is coming. Okay. 0, 0. Let's see 0, 0 now. So this is 0. This is also 0. So when this is 0, this becomes 1. This becomes 1. And here is 0. So this is 0. 0 and 1. Here is 0. Here is also 0. 0 and 0 will give you 0. So 0, 0 is going to give you 0. It is OR definitely. Now 1 comma 1. So now this is 1 and this is also 1. So if this is 1, then this will be 0. This will be 0. And from here this is coming as 1. 0 and 1 will give us 1. And here is also 1. 1 and 1 will get 1. Here is 1. This is OR gate. This is OR gate. This is OR gate. Okay. Like this questions will be asked from you. One more big question we'll try to make. Okay, all right. NOT gate we have attached. It's a single output, so one input, so we have to make one more input at least. So here is the input. Connect with OR. Okay. Then here also one more NOT. Then we'll bring this one. Okay. Here we'll connect with one AND. Then these two connect with one more OR. And in front we'll connect NOT. Okay. So here inputs are A and B. Suppose I want Y as 1. Find AV. Find inputs. So possible of inputs are what? 0, 1, 1, 0, 1, 1, 0, 0, right? So we'll make like truth table only. So AB 1, 0, 0, 1, 0, 0, 1, 1. Okay. You want Y is 1. You have to identify. Simple that is. Okay. First one is 1, 0. So you made this as 1 and this is 0. So if this is 1, you go this direction. Here comes 0. 1, this is not. So this comes 0. Okay. This is 0 already. So this is also 0. So here is OR. Here comes what? 0. Look at below. This is 1. So here is 1. Here is 0. So this is not. So here also become 1. 1 and 1. This is becoming 1. So here comes 1. So 0 and 1. Okay. 0 and 1. This is OR. This is OR. 0 and 1 means OR will give you 1. But there is not here. It will come 0. So 1, 0 when we took, Y comes out to be 0. Okay. So first one is not the answer. The second one will see. The second one, what is that? 0, 1. So this we took 0. This we are taking as 1. So when you took this as 0, this is not. So this will convert it into 1. Okay. This is 1. So here came out as 1. 1 and 1. This is 1. Now see here. This is 0. So this will be 0. Then this one. This is 1 here. Okay. Blue one at the moment. So this is 1. This converts it into 0. So this becomes 0. 0 and 0. Here answer is 0. So here goes 0. This is 1. 1 and 0. This is OR. It becomes 1. But this not makes it 0. So this is also 0. Okay. Then next one. Next one take 0, 0. So this is also 0 and this is also 0. So if this is 0, this goes over here becomes 1. This is 0, this is 0 only. So here comes 1. Here both are zeros. So this is 0, here goes it becomes 1. Okay, and here it becomes 0. So 1 and 0 will give you 0. So here is 0. Here is 1, here is 0. Again, this will give you 1 and this is 0. Now, which will be the answer? We know that. 1, 1. Okay, so our answer is, its answers are 1, comma 1. Right, students? So these kinds of questions will be there in logic gates and Semiconductors. So this is it. Semiconductors and logic gates are over. Now only one small, very small chapter is remaining, that is nuclear. Okay, now that also I'll try and finish today. So entire syllabus we have covered up. Okay, so today everything is over. Now take a rest today. Second and third, I'll post you 2 mock tests. Write them. Okay, today and tomorrow revise as much as you can. Second and third you write 2 mock tests, and again fourth day you revise, and fifth anyhow you have your exam. Alright, is that clear, students? Students, please respond.
Yes, sir.
Okay, students, then go and revise, go and practice. Don't worry, we are doing everything from our part, which is in our hand. We should do it to the fullest. Rest, keep it on the guard. Okay, he'll take care. However, what we will be capable, no, result will come accordingly. So forget about result, forget about everything. Just focus on your studies. How much we can do it. Keep revising as much as you can. Keep practicing as much as you can. Don't think about the exam at all. Okay? The result is not in our hand. What is in our hand is work. Keep working. Don't take tension, because tension will come only when you think about result. What is not in our hand, why to take care about that? Why to think about it? Just take care about what is in our hand. Study, practice. Keep doing. You should not have any time for thinking, overthinking, result and all that. Fully involve yourself in doing practice and studies. Okay. So all the best, students. See you tomorrow. I'll keep seeing you. I'll keep asking you. I'll keep talking with you people. Okay. Till 5th of the month. Right. All right then, students. Bye bye. See you then.
Thank you.